right? So now let's look at how to improve this robustness. Now we saw how these data sets are created, what kind of data sets, how they are created, C, R, A, AN, LI, all of them. How to use this data set now to study the robustness. Right, here is one example. So let's go through this two graphs here. So models with more parameters generalize to unseen situations, right? More number of parameters, which is it will be able to foresee unseen parameters and generalize better also. So let's look at this. X-axis or these are different models starting from ResNet 50, 121. These are different parameters, right? And if you see, these are errors that these models have, and lower, better is the error. So if you look at DenseNet here, which has the low error, so it's a larger number of parameters, that's what is mentioned here. More parameters, less errors. Similarly, in this case, ResNet 50, ResNext 50, ResNext on 101, again, this is large number of parameters, low number of errors, low amount of errors. And for any discussion on these graphs, if you want, feel free to come back. These are, I mean, our interest is to only look at how robustness is, right? Meaning, if you're interested, you can take a look at the paper or from where these results have come. But my intent here is to show that these kind of intuitions and conclusions as part of the content that we are seeing for robustness. Okay. On the right hand side, if you see, right, ResNet is here, DPN, ResNet X. DPN stands for dual path network. They actually have different layers. So larger models, more parameters, more redundancy in representations. One neuron fails, another neuron will pick up, detect the feature detected by another neuron. Right? So if one neuron fails, another neuron will pick up the feature and be able to actually add to the inference that is being made by the model. That's what is this unseen situation better if there are models or have more parameters. Right? So the baseline models are here, the large models are here, and large models make less amount of error. I hope that helps, gives you an idea for how these models perform. If you have any questions, please feel free to ask, and we'll be happy to answer any questions that you may have. Now let's look at some ways in which people have tried doing this, studying the robustness itself. Methods in which that they have tried. So Mixup is one method, right? Mixup augments the data by performing an element-wise convex combination. We'll see what convex combination is of input and output. Mixup improves the corruption robustness. Right? If you were to measure the robustness of any model, if Mixup is used while designing the model seems to do well. And here is an idea for convex combination. So given a finite number of points x1 to xn, and a convex combination of these points is a point of the form of alpha x1, alpha 1 x1, alpha 2 x2 till alpha n xn, and where alpha 1 is greater than, alpha I is greater than 0 and summation of alphas are equal to 1. That's the definition of what a convex combination is, but here is an example that I will show you. So, here is a image of a cat, image of a dog, and I want to do mix up between these two with my alpha being 0.7. And if you see, this is what will happen. Combined here, element wise combination. So, this one would get multiplied here, right. This one will get multiplied here. So, you will get an effect of 0.7 and 0.3 here. So, that's the mix up. If you look at the images, you'll be able to clearly see that there is some changes from this image and this image when you see this image. And the change is happening, meaning I'm sure we can actually try out this. I mean, if you're interested, you could try out this yourself also. By changing this value, the image that you're producing will be very, very different. Right? You could try from 0.1 till let's take 0.9 to see what happens. Some of these models have their code made public. Later in the module, I'll actually show you some methods where the code is public, Python code is public. You can try it out also. This is in terms of images, but if you just convert these images into, let's take audio signals, it's just simple mixing of audios. That's what an idea for mix-up is. Next, this idea for AutoAugment. AutoAugment proposes data augmentation strategies using diverse Python imaging library augmentations such as invert, solarize, and so on. These are example augmentations. We'll go through some examples now. Solarize is change the relative darkness of an image by overexposure. So, the idea of solarize is that you take an image, change the relative darkness of the image by exposing it to more light. Posterize is print or display a photograph using only a small number of different tones. So, you change only small parts of the image. That's posterize. Image contrast, if you change the contrast of the image, that's equalize. So, with these simple methods, you could actually see here that equalize, solarize, posterize, all of these methods have been applied to these images, and of course, some values are taken for these changes that are made, and the effect of that is on the output that we get. I hope it's clear. These are different methods. Some abstraction is that these are different methods. Think of these as some conversions that are happening. Let's take changing the brightness, reducing the overexposing to the light. All of this happen. Using all of this, you merge them and you get a different set of output. That's what auto-augmentation is. You augment the images with some methods, and you can use this output for testing the robustness. AutoAugment composes two augmentations together, each with two parameters, a probability of being turned on and an intensity. So, if you look at, let me show you the, right. If you see here, there is each with two parameters, a probability of being turned on 0.4 and an intensity of 4. Right. That's what is happening in solarize. Same thing, a probability of 0.8 and an intensity of 8 here. That's an auto-augment method. They train tens of thousands of deep networks to search for a few augmentation parameters, and they propose some of their best parameter settings wherever they're getting best results. That's what is shown. Okay, that's AutoAugment. Here is the random augmentation. In the earlier idea, the augmentation method is decided, right? You decide that you want to do equalize, you decide that you want to do posterize. Whereas here, to avoid AutoAugment's computational cost, because if you have to do all of this, there's going to be computational cost. Can we just use random augmentations? Random augmentations also will have computational cost, but is there a way by which you can actually reduce the computational cost and find a good method? To achieve diverse random augmentation, we would combine many random augmentations together. Controlled randomization can make images start to become unrecognizable. I think if it is uncontrolled. Let's take if you just don't control the randomization. Any random changes are allowed within a set of random processes. At some point in time, the image may become unrecognized, right? That's what that could happen. You have to be careful. So the idea is that you want to have a controlled random augmentation. Here, if you see, we took the same idea of AutoAugment, but we use random augmentation and mixes these random augmentations to keep the images recognizable. We randomly sample the operations, the intensity, the depth of each branch, and all the mixing weights. I'll walk you through what is going on. So if you look at it here, that's the original image, some translate happens, some shear happens, and then the weight for these two put together is also decided of 0.12. This is the image, and then some rotation happens. That is given a 0.2 weight. Posterize, equalize, posterize, and then a weight. All these weights are put together, all of them sum to be 0.8. So all of these augmentations are done, and the weightage for that output is 0.8. And then you also do a skip connection, which is, look, I don't want to do any of these augmentation methods. I will just directly use the original image also, and that is of 0.2. So now you get the AugMix output. Use different transformation, use only some augmentation methods, not all augmentation methods that are available. Does that make sense? Hopefully that helps in able to understand how AugMix works. So then next is ImageNet-C corruptions. So if you see avoiding train test overlap, you want to generate these AugMix outputs, and first to get a sense of the difference between ImageNet-C corruptions and the AugMix is very visible, right? If you see here, you can clearly see that the AugMix output is better than in terms of corruptions, better in terms of being the image is able to be recognized, but still have all the properties that we want to see as part of the augmentation methods. Yeah. Now let's look at an idea called PixMix. PixMix mixes training images with images from another data set for example, this is the other data set here, this is the input image, and then some random image from here is chosen to be added here, and then augmentation image, augmentation method, posterize that we talked about happens here, and then another image mixing is happening here. PixMix mixes training images with images from another data set. The bird training image is mixed with an image from a fractal data set. Right, so here is the fractal data set. This is random images in that can get added to the augmentation methods. Unlike Mixup, the mixing set is not the original training data set. Right. So if you remember in the Mixup idea, right, Mixup idea, all of these are from original data set, whereas here what we are doing is the mixing set is not from the original data set. This is a different set. As I said, some Python code that could be used for some code that could be used for playing around, which is idea of augment that we said, randomized choice from somewhere from these methods, and Mixup, random choice, additive, multiplicative. Again, all these things that we saw until now is available here in terms of a code that one can play with. PixMix evaluation. Earlier I mentioned about, look, I'll show you some tables which can help you understand how these methods are evaluated. What should you look for, right? I think these methods, the goal is that we should not lose the accuracy, but the goal is our safety and robustness should increase. A metric that we use to measure robustness should increase. Hopefully, the accuracy and other metrics will stay as is, or not all methods have stayed as is, but it can have a small effect on the accuracy, but the safety should increase. PixMix helps with robustness as well as with other safety metrics. Here is how the idea is. This is a baseline image. This is the cutout image. Parts of the image is gone. This is the Mixup idea, the cut mix idea. So I put the idea, meaning a small image here to help you understand. Original image, Mixup, the dog and a cat getting mixed. Cutout, a part of an image is taken away. Cut mix this is how it will be. Cut and mix, cutout and Mixup idea put together would be cut mix. And this is the PixMix idea that we saw a couple of slides back. What are the things that are measured? So this is the error, adversaries error, consistency, calibration, and anomaly detection. Don't worry about these errors. So what my intent here is to show that if you measure these metrics in different methods that we have seen, the PixMix method does well. If you see here, they do well across multiple metrics, and note that many of these methods do not improve typical accuracy. They just improve safety metrics. What does it mean? So let's look at some of the things that has happened, right? If you look at here, the anomaly detection values, so the PixMix has improved by 11.6, right? And consistency is dropped. So essentially the idea is that PixMix method is doing well across these different methods, and particularly they are good at the safety metrics. As part of the robustness idea, we'll also look at this idea called as distribution shifts. Distribution shifts will come into handy when we think about robustness, and when we also move to the adversarial attacks, it will help you to build on this idea of distribution shifts. Distribution shift idea is that the train, right? Train is on a particular data, the test is completely different. The distribution is shifted. That's the idea. Distribution, if you treat this as a distribution, it is shifted from here to here, and that's the problem we will study. And why is this important? What is the problem? What are the different ways that the distribution shift happens? Distribution shift occurs when the joint distribution of input and output differs between the training and test stages, which is P train X and Y is not the same as P test X and Y. This issue is present to varying degrees in nearly every practical ML applications, in part because it's hard to perfectly reproduce testing conditions at the training time. I think we've seen enough examples. The Waymo slide that I showed you, where pigeons are there, a signal and a fire extinguisher on the street. All of this is not something that while training the model would have seen. Different types of distribution shifts. Let's just look at one idea called covariate shift. Here, if you see, this is training data, this is test data, that's the learned function. Because of these blue points, the learning that the model learned only, that's the function, whereas the target function is this one. I'm sure you would have started thinking about why this is happening, but let's how to explain it. But here is what it is. P of X changes between the train and the test, but P of Y given X does not change. Right. Covariate, that's the idea here. When the distribution of the training data and the test data differs significantly, a learned model can fit training data well, but perform poorly on the training data. I think this line is probably applicable for all types of distribution shifts. Here is an example that we said, driverless car, sunny streets, it was trained on, but snowy is the test, snow is the test phase. Native English speaking is the train, whereas test on English speaking, native English speaking, test on all English speaking. Right? I trained it on only native English speaking speakers, whereas I tested it on all English speaking, including me. Right? I'm sure there are other examples that you can think of. If you can think of some interesting examples where these covariate distribution shift happens, please send it to us. It will be interesting to see. And the main thing that you want to keep in mind is this. P of X changes between train and test, but P of Y given X does not change. I think that you can see in this graph also. Making a shift, I mean, we'll also see something opposite to a covariate distribution shift, but let's do another idea called concept shift. Here the train is this distribution, test is this distribution. You can already see where I'm going. So here is what the model trained to classify. Let's take if this was classifying an image classifying an image into two categories. Here is the model that is trained here. But I'm sure you can look at this and already have some understanding of what the concept shift will be. But let me explain it. Two-class data set with two-dimensional features. That's what is represented here. Classes color-coded in red and green. Purple is the decision boundary. So yeah, classes, boundary, input distribution exactly same as in the train. If you have not already seen, in terms of data points, if you see, they're exactly the same. If you look at these two, right, and this two, the distribution is exactly the same, right? Whereas the decision boundary has just changed. That's why it's called concept shift. The input distribution exactly same in the train and the test, but the relation between them, the decision boundary changes, right? For example, in this case, you could think of it as a two-class, so it could be like a cat and a dog, and it could have changed, right? Any other examples that you can think of? So here are some examples that I can walk you through. Browsing history from pre-pandemic deployed in March 2020 for purchase recommendations. If you think about it, right? People, whoever had browsing, meaning if you were to look at all the browsing history of pre-pandemic state, March 2020, and then you say that, oh, look, using this, let's just do some recommendations, right? The data points, all the kind of browsing people would do, right, before and after would have changed, right? And the effect of this training will not be there, right? In the concept shift here, this example of pre-pandemic browsing history used for purchase recommendations will not work. I'll give you another example also. Watching travel videos would imply might buy plane, hotel tickets, pay for nature documentary movies, all of that, right? Is that possible? Will the meaning in this case also concept shift will happen, right? Watching travel videos, I watched lots of travel videos. Does that mean I would actually buy a plane ticket, hotel tickets, and actually do buy documentary movies also? Think about it and process it for how concept shift is applied in these examples. If it's not clear, come back, we can actually discuss it. Here is the one that I shared is different from the covariate shift. Different types of distribution shift, prior probability shift, label shift, all that. Reverse of covariant shift, which is prior probability shift appears only in Y leading to X problems when we believe that Y causes X. It occurs when P of Y changes between the train and the test, but P of X of Y does not change. Right. This is opposite to what we saw here, right? Opposite to covariate what we saw here. Any examples that you can think of? Here are some examples. Train on the data, meaning medical diagnosis. If you see, train on data to predict diagnosis given symptoms. Test on data during flu season, where test of flu, right, and train of flu. Test of flu is greater than train of flu is because you're testing it during the flu season. Right? So this is because of flu season. And while the flu symptoms, P of symptoms given the flu is still the same, meaning everybody is coughing, everybody is sneezing, the symptoms have not changed, right? So that's why if you see, that's the connection here, and this is, right, there is a relationship between flu and symptoms, and the training phase was done in a normal condition, whereas test phase is done when the flu season is happening, and that's why this is a probability shift or a label shift. Detecting these distribution shifts are interesting or hard also sometimes. And generally, I think as ML developers, we don't really keep all of this in mind while we do the development of these models. So the goal should be, where is this robustness coming? The goal should be monitor the performance of your model, monitor accuracy, precision, statistical measures, or other evaluation metrics. If these change over time, it may be due to distribution shifts. Right? You want to keep that in mind. Monitor your data. You can detect data shift by comparing statistical properties of training data and data seen in deployment. Right? So data seen in deployment is very hard, but at least you can compare whatever the training data to the metrics that you have, and while testing also. This distribution shift is actually a pretty important and a large topic. So there have been actually workshops also on this topic. Here is one quick example of a workshop at NeurIPS. Distribution shifts, where a model is deployed on a data distribution different from what it is trained on, pose significant robustness challenge in real-world ML applications. Such shifts are often unavoidable in the wild and have been shown to be substantially degrade the model performance in applications such as biomedicine, wildlife conservation, blah, blah, blah. What they are asking is topics that they're interested in. The point I'm doing, showing this image from the website of this workshop, is that to tell you that how important a distribution shift and what are the different problems that at least this workshop was trying to address. Examples of real-world distribution shifts in various application areas, methods for improving robustness to distribution shifts. If the distribution shift happens in the data, what all methods you can do to reduce it, reduce the effect of it. Empirical and theoretical characterization of distribution shifts. Can you characterize covariate shift? Can you characterize the label shift in the ML model that you're developing? Benchmarks and evaluations. Okay. Yeah. Thank you for listening to this module. Hope to see you soon.